Uh, can someone please confirm if I'm audible? Hello, am I audible, guys? Yeah, thanks. So yeah, maybe we can start today's live session. So welcome to the live session for week 8 for the course Digital Circuits, which is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. And I'm Anant Singhal, a PhD student from IIT Jodhpur. And today again, I'll be assisting you in solving some of the similar assignment problems that have been assigned to you for the week 8 assignments. So yeah, I think we can go to the course outline. So yeah, for those who are attending regularly, they might be knowing that we have kind of already covered. Yeah, just give me. So in the last lecture only, we have covered some of the counters and shift registers. I mean, most of the part of that, and we were only left with the finite state machines from the last lecture. So you also might have seen that in your V-Gate assignments that have been given to you, all the questions are related to the data converters. That is basically the week 9 topic that are the all the ADCs and the DACs. So we'll be covering both of these problems or both of these important topics in this particular lecture. And I think in the next week subsequently we might be starting up for the memories part. So yeah, we'll see that, and let's start with some of the problems. Just give me a minute. Yeah. Okay. Okay. So we have our first problem, which is very basic and theoretical type. So I'm assuming that you have already gone to towards the lecture of the VGate assignment that are mainly based upon these ADCs and DACs. So I'd like to uh, I hope you will be interactive and let me know the answers quickly for the basic and theoretical questions. So this is one of the basic question which says which of the following options represents the fastest analog to digital converter. So as the name suggests, these are analog to digital converter. That means the input of these. So let's say we have something, some box. We are giving some analog input. By analog, what do we mean by analog? You might have heard analog and digital watches, right? So analog means like the finite values. You can say for very basic terms, you can let's say we are giving some decimal input and we are getting some binary output out, and which is nothing but digital. So this box is nothing but a ADC. And if the same thing happens backward, so that box will be called as a DAC, that is a digital to analog converter. So we have different types of ADCs and DACs. So we'll be covering most of them in this particular lecture. So for this particular type of question, we have all these types of ADCs, that is counter type, flash type, successive approximation, the resistor type, and dual slope type. So I mean, just to cover the basic, so in this particular problem, what do we have is the flash type ADC is the fastest ADC, that is, I mean, some theoretical part. And why it is very fast? Because for this particular ADC, what do we have? We have multiple comparator for each bits. So all of these ADCs are built using comparators. We'll see some of the operation if possible. So for this particular ADC, n bit, let's say n bit flash type ADC contains 2 raised power n minus 1 comparators. For example, what I want to say is, let's say we have 4 bit flash type ADC, so that will have 15 comparators to make with. So due to the parallel and the fast operation, this is the fastest type of ADC, and at the same time, this is the costliest or the expensive ADC, because we require a lot of comparators and it is exponential towards the cost. So more comparators we have, higher the amount of, or the higher the cost for the particular ADC. So like, yeah, so I'm continuing on that question. So the next question says which of the ADC is more expensive. So that is why the correct answer would be flash type ADC. So we'll see some of the problems related to ADCs later, and we'll see how they work. But for these two problems, you should be knowing that the fastest ADC that we have is a flash type ADC, and for n bit flash type ADC, we have 2 raised power n minus 1 comparators. I hope this is, I mean, this is the basic thing only, so it should be clear. So let's go towards some of the questions for both ADCs and DACs. Okay, so this is the first problem like first numerical problem we have for today, which says for a 3-bit weight register DAC. So this is the particular problem. What can be the values of R0, R1, R2, and RL? So can someone please confirm if they have read about this? I mean, in the lectures or in general. Does anyone know about this particular DAC? Okay, great. So maybe you can try out and let me know your answers in the chat box. That is great that some of you already know about this DAC. So let me try to explain till then, and you can type your answers in the chat box, those who know. So uh, DAC, as I said, it is nothing but a digital to analog converter. So what do we have is we have some digital values. For example, in this, you see there are different bits assigned. So let's say this is V0, V1, V2. Let's say we have different bits assigned, which can be 0, 1, 0. So this is the LSB, this is the MSB. And this gives you some analog output, let's say 2 volts, something like that. So that is basically a digital to analog converter. And the basic working of this is, okay, let me explain or let me make it out. So what do we have is, let's say we have the analog output, which we are calling as VA. So the first register that we have is having a value of R0. The second register that we have is, let's say, having a value of R1. The third register that we have is having a value of R2. So the closest to the output or the analog output is always the LSB. And let's say this is dot dot, and let's say this is going up to nth register. The last register is the MSB. And apart from this, it also has a load register, which is what we call as RL. And for this particular circuit, you already might be knowing that the value of R0 is nothing but, let's say if R0 is R0, then what do we have is R1 is R0. Okay, so let's say we keep it maybe more generic. Let's say R0 is R, so R1 always comes out to be R by 2. R2 comes out to be R by 4. Similarly, R is for N. Okay, wait. There's some problem with the screen. Similarly, R is for N will come out to be R2 raised per N. And for this particular circuit, R is very, very, very greater than R naught. In general, we see that RL is at least 10 raised per 3 approximately times that of R naught. That is 3 orders higher than of R naught. So as you can see, I mean, this is the basic of this particular tag. As you can see, for all the options, the first value, that is the value of R naught, is same, which is nothing but 100 kilo ohms. So let's say we keep it as 100 kilo ohms, which is R. So it is the same circuit, which is the first bit is LSB, as I said, the last bit is MSB, and we have this load resistance at the last, which is represented like that. I hope that you know this notation, because we can also make it something like this, which is RL here and ground this. This could be the same thing. This is just a basic network only. So by this, we can say that R1 will be 50 kilo ohms, R2 will be 25 kilo ohms. So since there are only 3 bit, so it only has 3 registers, that is R0, R1, R2. So we have come to know, and the value of RL will be very, very greater than 100 kilo ohms. That is what we can see. So from the given options, we can see, okay, only one option is following the trend, that is option B. So R1 is 50 kilo ohms, R2 is 25 kilo ohms, and RL is in mega ohms. That is approximately greater than 3 orders of R0. Is this question clear to everyone? Yes. Is there any doubt? Oh, great. So let's move ahead. Okay. Is there any doubt again?
Yeah, can you explain the concept? Like the potential should be the same, right? That part.
Potential should be.
And how are you going to get this particular R by 4, R by 2 thing?
Yeah, yeah. So, okay. So it is equivalent to, okay, let me try to explain that too. That is actually a good question. So basically, if you see that in every binary bit, what do we have is, for example, because we are taking, maybe I can give you an example that will clear your doubt. So let's say we are taking, for example, here 0 1 0 only, right? I just took that 0 1 0. Sorry, this is not 2, this is 0. So you know that when we are doing the binary conversion, sorry, binary to decimal conversion, what do we do is we multiply this 0 by 2 raised power 0, then we do plus 1 2 raised power 1, then we do 0 times 2 raised power 2, right? So if you are doing the opposite conversion, so what I basically mean now is, let's say a 15 volt of, not a 15, yeah, let's say a 15 volt will correspond to something like 1 by 2 plus 1 by 4 plus 1 by 8 plus, yeah, I think, yeah, that would be it, something like that. So this thing, let's say if I even write 15 16, so it will be 8 plus, I think it will be 15 by 16. So this is the actual conversion of that 15 by 16. So that is why every register is getting halved as we are going ahead and ahead. I mean, that is why we are trying to halve the register every time, because we are trying to relate it with the every binary conversion. I know that it might be, you might be thinking that this is nothing but 2 plus 4 plus something like that. Sorry, 1 plus 2 plus 4 plus something. But in reality, what we are doing is we are doing the digital to analog conversion. So that is why we are doing the register. We are halving the register instead of doubling the registers. Does it make sense?
Yeah.
Yeah. So later you will see some of the numerical examples that will clear that why we are doing this R and 2R. Sorry, halving by one bit. Okay. So the first type of DAC that we saw was a weight register DAC. So we have one more deck that we have in our particular lecture, that is R2R ladder deck. So in this, what do we have? We have a combination of R and 2R again and again. So you see R2R, R2R, and so on. So that is why we call it as a R2R ladder network. And this is the output, analog output again. So this is the output. So in this particular question, it says that the value of RF is equals to R, which is the reference register. The value of reference, okay, so Vref, it's given as 10 volts. RF, it's given as, what is the value of RF? Okay, it's R only. And then we have, it says if the analog output, that is the value of VAA, is 9.37, what is the binary input from V3 to V0? So V3 is this thing and V0 is this thing. But this circuit is again connected to a binary to gray converter. So let's say this particular thing is a box, for example, just forget about this particular box. So this will be, let's say I'm calling this as V0 dash, this is V1 dash, V2 dash, V3 dash. So we can easily calculate what is V0 dash, V1 dash, V2 dash, and V3 dash. And then we can do, let's say we get this thing V1 dash, V2 dash, V3 dash. And let's say if we do a gray to binary conversion for this particular bit, then we'll get V0, V1, V2, V3. And yeah, just to be clear, the V3 is the MSB, so we should have written it in the opposite way. So the actual answer will be something called as V3, V2, V1, V0. So let's try to solve this out. So the resolution for a R2R ladder network you might have already seen in your theoretical lectures. For a R2R ladder, the resolution is nothing but the reference voltage divided by 2 raised power n. That is 10, and it is a 4-bit register, so it will be 10 by 16. And the output voltage, that is V out, for this particular question, which is VA, it's nothing but resolution times V in. Or we can write this as, to be precise, the final formula will be V2N times V in. So this is your output voltage. Now question has already given that the output analog voltage is 9.37 volts. the reference voltage, and we have just calculated the resolution. It's 10 by 16, and we need to find the input voltage. So yeah, I think you can do the basic maths from this. Can anyone tell what is the Vin that we are getting? Just 5, just 8. Okay. So we are getting a Vin of 15 volts. So basically, we have the input of 15 volts. So we need to write, first of all, that in digital. So V3, V2 dash, V1 dash, V0 dash. It should be 1111. That is a decimal equivalent of, sorry, not. So I can write this is to the base 2 and this is to the base 10, right? But the final answer, it is asking about the values of V0, V1, V2, V3, not about the input of this tag. So we need to do a gray to binary conversion. So I hope you already know how to do the gray to binary. So please let me know the answers in the chat box quickly. So let's say this is gray, and if I'm doing, maybe I'll write here gray to binary. So how do we do that? We keep the first bit same, that is 1, and then we do the XOR of the next bit. Sorry. So XOR of this and this will be 0. Then we do the XOR of this and this, that will be 1. Then we do the XOR of this and this, that will be 0. So the final V0, oh sorry, V3, V2, V1, V0 will be 1 0 1 0. Which is option, is there any? Sorry, I'm having some glitch in my screen. Yeah, which is option A. Is it clear to everyone? Okay, let's move ahead. Okay, so we have a problem then, a 16-bit DAC. So we have not like given what type of exact DAC it is. Is it a binary weight or a, let's say, R2R? So you can consider any, because the only difference between the resolution is like it's pretty less. So let me let you know that also. So for, as you can see, for a R2R ladder, we just saw the resolution for the same was Vref times 2 raised power n. So for all the other DACs that we have, that is the binary and all the other DACs, the resolution is nothing but Vref by 2 raised power n minus 1. So this is the only difference, and if you calculate that in decimal, that will be very less. So if nothing is given that what type of DAC it is, you can assume it to be maybe R2R or a, let's say, this uh, binary weight DAC also. So considering maybe that, please try to solve this problem. I have already given you all the formulas. You just need to calculate uh, what is the output of this particular DAC. Do you want to try, or shall I do it by myself? Sure, sure. Go ahead and let me know the answers. Okay, so we have got one answer as so I've got an answer as C. So let's do that. So we have the input of this DAC, which is given in hexadecimal, so we can convert that. Yeah, so DC to the base 16. So did anyone convert it to decimal? Can you let me know what is the decimal equivalent of this thing? Anyone? So it will be 16 times 16 square, that is 256. 56, then E is 15 times, sorry, E is 14 times 16 plus C is 12. Okay, 3744. Because I've got different answers. Okay, I need to calculate it myself, I think. So it's 460 plus 16, 14. Okay, so I'm getting 3564 to the base 10. Okay, so please check your answer. I'm not sure. Someone's written 3744. Please check your answers again. So if 3564 is the basically the decimal input of this particular thing, then we can write the output voltage, which is nothing but the full scale range divided by 2 raised power n minus 1 times V. So full scale range is already given, it's 8. Then it is a 16-bit DAC if I'm not wrong. So it's 2 raised power 16 minus 1 times 3564. So again, you can use your calculator. So 2 raised power 15, I think it's 65535. 8 times 3564. So it's 83024. It's somewhere close to half. Yeah, so it's coming out to be 0.435 volts, which is option A. No, sorry, option C. Is it clear to everyone? Okay, let's move ahead then. So we have just talked about the flash type ADC. So please let me know your answers in the chat box. This is a very easy question. So just let me know what do you think is the answer. You can take 1 minute or so. So it says we have a flash type ADC and we need to find the relation between the number of comparators and versus the number of bits for the flash type ADC. We have already got the answer, which is A. So let's see. So as I said, for n-bit flash type ADC, we require 2 raised power n minus 1 comparators. So 3 we can directly neglect because it is saying it is constant, so that is not possible. So for 2, what do we can see is for 2 comparators, we need, sorry, for 2 bits, we need 3 comparators, which is fine. For 3 bits, we need 8 comparators, sorry, 7. Okay, which is wrong. So option 2 is also incorrect. Oh, yeah. So only option left is 3. So yeah, it's on a very small axis. So maybe just to confirm, we can check for 8. So for 8, we require 2 raised power 8 minus 1, which is 255. And it is approximately that only. So option A is the correct answer. That is figure 1 is the correct answer. Is this clear to everyone? Okay, let's try this. So have you already read about how a SAR ADC works? So we have few questions about the ADCs now. Do you already know how does a SAR ADC works? Okay. Fine. So let me try this problem with myself and then I'll give you a similar problem further. So in this question, we are given that we have a 8-bit SAR ADC. That is nothing but a successive approximation register type ADC. And this 8-bit ADC is used to convert 4.75 to the digital output. That means the input of this ADC is nothing but 4.75 volts. The reference voltage, again the Vref, is given at 12 volts. The output, it is asking that the output of the ADC at the third clock, sorry, at the end, so end is a very keyword here, at the end of third clock pulse after the start of convergence. Okay, so we know that the resolution of any ADC, we just wrote that it is nothing but, okay, is nothing but Vref by 2 raised to power n minus 1. So we can easily calculate that it is a 8-bit ADC, so n is 8. So we can write the resolution to be Vref is 12, 12 divided by 2 raised to power 8 minus 1. That is 63, no, 12 2 raised to power 8 minus. So, so it's 12 by 255 basically. If you do it 0.047. So this is the resolution. So now how does a SAR ADC works is, so at initial clock, that is at the first clock, which is clock 0, I'm naming it has all the bits. So since this is a 8-bit ADC, so it has all the bits as 0. 1, 2, 3, 4, 5, 6, 7, 8. So this is nothing but the MSB, this is the LSB. So now how does a SAR ADC work is, we do at every application of clock. So at the first clock, what we do is we make the first bit as 1. So what I mean to say is, I'll let you know the operation later. For let's say if we had a clock 2, then we'll make this particular bit as 1 and the rest of them as similar. So now there is a condition that we check at every clock. So for example, let's say at clock 1, what we'll do is we'll check what is the actual output that we get at the clock 1. So this is nothing but 2 raised to power 7, right? So this is 0, 1, 2, 3, 4, 5, 6, 7. So the output for this clock will be 2 raised to power 7 times the resolution, which will come out to be 6.023 volts. So now there are two conditions, since we already know that the output of this ADC needs, sorry, the input of this ADC is 4.75. So either it will be greater than or either it will be less than. So if the calculation or if the input is greater than that of 4.75, then what we'll do is we'll discard the one. So basically if V is greater than V in, then we discard the one. I hope you are trying to understand this, because if we keep this one, then your final output will always be greater than that of the given value, right? We want such digital approximation so that our final output will be close to this decimal value. And if you keep this one always, then the output will be greater than this, right? So what it will do is we'll discard this one and we'll at the next clock cycle we'll make this as 0 again. And if it would have been V less than Vn, then we'll keep the one. Is this thing clear to everyone? This is the main criteria that we need to follow. Okay, that is great. So yeah, so for the clock one, we need to discard the one. So let's talk about clock 2 now. So at clock 2, this will become 0 and then this will become 1, right? 0, 3, 4, 5, 6. Now the output for this will be 2 raised to power 6 times 0.047, which is coming out to be 3.011, and which is less than that of V in. So what we'll do is, for this case, we'll keep the 1. Now we'll go for clock. So now we'll go for clock. Just again, sorry. We'll go for clock 3 now. So 0, 1 will remain intact, and now this will remain 1, will become 1. So it's 0, 1, 1, 0, 0. So now, as we have seen, the question clearly says that we need to find the output at the end of the clock 3. So if it would have been written at the start of the clock 3, then this would have been the answer. But we need to find out at the end of the clock 3. So we need to process it once more. So if I do the calculation, so this will be 2 raised power 6, which is nothing but 264 plus 32 is 96, right? 96 times 0.047. It is coming out to be 4.512, which is still less than 4.75 that is given in the question. So what we'll do is we'll keep this one, right? So at the end of clock 3, 0, 1, 1, 0, 0, 0, 0, 0. This will be the result. And let's say if I talk about clock 4 also here. So if the question would have said at the start of clock 4, then the answer would have been 0, 1, 1. Then this bit we would have changed to 1 and all the others as 0. So this is start of clock 4 and this is end of clock 3. Is this clear to everyone? Okay, so the answer is 0, double 1 and then all zeros. So is there any option like that? Yeah. So option B is the correct answer. I'm hoping it is clear. If there is any doubt, please let me know. Okay, so I'm assuming now it is clear. So let's try this question now. This is a similar question. Now the question says we have a 7-bit ADC. We have an input of 8.95. We have a VREF of 10 volts. The output at the start of fifth clock. So this is exactly same question. You just need to work one by one and let me know what is the answer. Is the question clear to everyone? Okay, just try out. Maybe take 4 or 5 minutes and let me know the answers in the chat box. Okay, so I've got one answer is D. So I'd like to give you a hint that it says at the start of fifth clock. That means you need to process the fifth clock also. I mean, not process, but you need to make that bit 1 also. I mean, by seeing that only, I can see that option D cannot be the answer, because if it would have been the answer, then the fifth bit, that is 0, 1, sorry, 1, 2, 3, 4, 5, this should have been 1. Okay, so I got one answer as C. Let's wait for maybe one more answer and then I'll also try it out. Anyone else? Any answer? Hmm, if it is the start of yeah, so after you process that clock, it will check the condition. I mean, the way it works is you have to put 1 initially and then check the condition. Okay, so let me try it out now. So it's again the similar way. So for clock 0, let's say I write again. So this is a 7-bit ADC, 0, 1, 2, 3, 4, 5, 3, 4. Yes. So this is the clock. So let's say I apply the clock one now. So it will do this one. It will check now. So what do we have? Okay. I need to calculate the resolution. Can I even tell what is the value of resolution coming? So it should be 10 by 2 raised by 7 minus 1, which is 0.8 cannot be the answer because it should be, yeah, should be 0.078. So I'll check this now. So this should be 2 raised by 6 times 0.078, which is uh, 5.03, and it is less than 8.95. So we'll keep 1. Clock 2, the 1 will keep the same. The clock 2 will make one more 1. This will be 64 plus 32, that is 96 times 0.078. This will give me 6. So will give me 7.5 something, which is still less than 8.95. So what we'll do, we'll keep the 1 again. So at clock 3, we have 1, 1, and the clock 3 will make this as 1. Now we'll again check. So 96 plus 16, it's I think 16, it's 112. So it's again, what is this? It should be 8 point something. 8.81, I think. So it is 8.95. It is still less than that. So we'll again keep 1. So clock 4 will have 1, 1, 1. The fourth will be 1 also. Now we'll check it. So it's 120 times 0.078, which will give me, I think, 9 point something, I'm sure. Sorry, so it is now greater. So what we'll do is we'll discard the 1. So that means at clock 5 we have 1 1 1, we have discarded the clock 4 and the fifth bit will be 1. So this is at the start of clock 5. This will be the answer. So is it clear to everyone? Which is option, yeah, option C is the correct answer. Okay, if this is clear, let's move ahead. Okay, so this is a very simple question. We have just done that. So now we have a deck which is R2 R ladder deck. The input is given, the reference voltage is given, you just need to find the output. So output will be nothing but resolution times the input, right? So just try it out and let me know the answer. So this is just basic calculation. I've got one answer as C. I'll wait for one more answer and then I'll also do it. So I've got B now, okay. So I'm getting different answers. This should have not have been the case. This is a very straightforward question. So V in is nothing but resolution times V in. So resolution will be VREF. VREF is given 20 by 4 bit is there. So 2 raised to 4 times V in is what? 1011. 1011 is 8 plus 3, 11. So it's 20 by 16 times 11 by 4. 55 by 4, it's 4 1 3.75. Yeah, option B is the correct answer. I hope you have corrected. Yeah, option B is the correct answer. Okay, a similar question again for, please let me know the answers quickly. This is a similar question. So I got one answer as B. So let's see. So it is again very straightforward. So V out is E ref by 2 raised power n times V in. Oh, so we need to find V ref in this question. V out is 5 volts. V ref we need to find. It's a 4 bit. V in is, oh, input is 1001, which is 9. So V ref will be 16 5, that is 81i. So it's 8 ja, 72. Yeah, 8.89. So option B is the correct answer. And the negative sign if you are worried about L. So the actual circuit of the DAC R2R ladder also has a op amp at the end. Let's say this is R2R and we have a connected op amp. So if you know the non-inverting op amp has output V out as minus RF by R times V in. So hence this negative signs come. So maybe I do have a, I think a picture of that. Yeah. So this is actual R2R ladder. So the output of this is connected to a op amp to the inverting terminal, and the output, the final output of this op amp is minus RF by R times V in. Hence the negative sign is given in the question for the output. Okay, let's see this. So it says if the resolution of the digital to analog converter is approximately 0.4% of its FSR, then it is a, okay, this is actually a good question and a very basic question. Please try to solve it by yourself and then I'll also try to solve it. Maybe you can take 2-3 minutes and let me know what is the answer. This has got one answer. Let's see. So this is again a very easy question. Just some tricky language is used. So it says if the resolution of a DAC. So resolution is nothing but. So again, it's not given what type of DAC. So we'll consider it. Let's say any other. So it is nothing but full scale range 2 raised power n minus 1. And it says this is equals to 0.4% of the full scale range, right? So basically this is equivalent to this. So from this we can easily calculate n. So it is FSR 2 raised power n minus 1 is equals to 0.4 by 100 times FSR, and this will give me, so this is, sorry, 0.4, so this is 0 250. So this is 250 is 2 raised power n minus 1, which will give me 2 raised power n is equals to 251. So what is the minimum bits that we require to represent this 251? We need to check that. Okay. So 2 raised power n should be greater than 251, right? Implies n, if let's say, what is the option? So minimum option is 8. So let's say if I keep 8, so 2 raised power 8 is 256, which is greater than 251. So it is actually a 8-bit converter. So option 3 is the correct answer. Is this clear to everyone? So let's move ahead then again. Okay, so it is again a very simple problem. It is just given in the form of a circuit. So it is a R2R ladder network with B4, B3, B2, and B1 all as one. So basically what it is saying is this is one, this is one, this is one, this is one. Vref is also given. You need to find out the output. That is the negative of this. I mean, this is the output. So just try it out. Maybe take 1 or 2 minutes and let me know the answer. Okay, I've already got one answer. I'll wait for some more answers and then I'll also solve it. Maybe 1 or 2 minutes. Okay, all of you are saying A. Great, so let's see, yeah. So the input is 1111, that means the V in is 15 volts. So V out will be minus RF by R times V in. So RF is equals to R only, so basically minus V in only. So V in we can calculate, it's minus R by R will cancel out, so it's Vref times. Okay, so everything is 1, so we can also do that 1 by 2 trick that I told you in the initial class, those who saw asked the doubt. So it will be 1 by 2, B2 by 4, B3 by 8 plus B4 by 16. Since we have 4 bits and all of them are basically equals to 1 only, so we'll add them up. So it's minus Vref is, what is the Vref? Vref is 8 volts times, so all of them are 1, so I'll keep the 1. So this is I think 15, right? 8 2 ja. This will give me minus 7.5 volts, which is option A. Yeah, option A is the correct answer. So if this is clear, let me know the answer. Okay, wait. Yeah, let me know the answer to this. Maybe, yeah, do this question first. Okay, wait. Let's do this only first, and then we'll see the next. Again, take 1 minute and let me know the answer. This is very easy. So I've got some answered. So yeah, it's very straightforward. So the resolution is nothing but Vref by 2 raised per n for this R2R. So Vref is given, yeah, Vref is 5 by 2 raised per 8, 5 by 256. Is it D only? I mean, so it should be 0.0, very close to 2, I think. Okay, I'm assuming it's very close to 2, I know, but I'm assuming it's 19 because option D says that, which is nothing but 19.53 millivolts. So option D is the correct answer. Please quickly let me know the answer to this. So in this, please be clear that the MSB is 1 and it's increasing at every resistance. The LSB is 8. Try it out and let me know your answers in the chat box. Maybe take 2-3 minutes. Can you answer? This was very simple. Okay, let me solve it then. Okay, so we have V out again as minus. Okay, so we have 1 kilo ohms of resistance. So basically, oh, we need to find out the V out, right? So V out is, yeah. So we can, since we have different resistances, so we can apply maybe a KCL here. So let's say this is the current I and this is RF. So V out is nothing but, because the current is minus I times RF. In the overall current, if I apply KCL, it's Vref times, so it's A by 1 kilo ohm plus B by 2 kilo ohms plus C by, so this is the voltage that I'm writing. I mean, this is the actual current level. This is 4 kilo ohms plus D by 8 kilo ohms. So yeah, I can calculate this. So Vref is it given? Assume logic one has a, yeah. So V reference is 2.5 volts and it is 1010. So it will be 1 by 1k plus it's 0, 1 by 4k, and the rest is 0. So I can calculate the I as 2.5 times 4 plus 1, that is 5. So it's 1.25. So it should be 3.125 milliamps. And you know the RF is already given to you. So the output voltage will be minus I times RF, which is 3.125 times 1 kilo ohms. So this is milliamps. So milli and kilo will cancel. So the output voltage will be minus 3.125 volts, which is option C. I hope you know the working of an op amp. So what happens is if this is 0, then this is 0. So the whole current goes through this. So if you apply a KCL here, so let's say this node is V, for example. So V minus A by R4 plus dot dot dot, it will be equals to V minus, sorry, will be equals to V minus V out by RF. I hope you know how to apply a KCL. That is a basic network thing. Is it clear to everyone? Great. Yes, is there any doubt? Please let me know if there is any doubt.
No, sir, nothing any doubt.
So we have how many comparators are required for a 3-bit. So this is again a straight question. So we require 2 raised power 3 minus 1, right? That is 7. So A is the correct answer. Hmm. Okay. So we have one more type of ADC, which is single RAM type ADC. I'll not go very detail into the theory of that. So it is basically an integrator type ADC which has a resistance and a capacitance. So let me just let you know. So it has a resistance, capacitance, the input voltage is given, it has a frequency is given, the ADC generates the digital output of this, then the find the ramp voltage. So I'll give you the direct formula to calculate this. So the ramp voltage is nothing but slope times number of clock cycles times time period of the clock. So yeah, just you need to just apply all these values and you'll get, and the slope is nothing but V by RC. So let me calculate the slope first. The input Vi is given, yeah, 3.5 millivolts. R is given as 2 kilo ohms. C is given as 0.5 nanofarad. That means minus 9. Minus 6. This will be plus 3. So this will be 1. Okay, so the slope is nothing but 3500. Okay, yeah, 3500 if I'm not wrong. Please recheck the calculation once. I don't know. So the ramp voltage is slope, which is 3500 times number of clock cycles, which is 512 as given in the question. It has 512 clock cycles, and the period is 1 megahertz. Sorry, the frequency is 1 megahertz. That means the time period is 1 by 1 megahertz. That is 1 microsecond. So I'm making it 1 microseconds, not right seconds. So yeah, we just need to calculate this, and that will be our answer. So can someone quickly calculate and let me know? So it should be half of 35, that is 17. Yeah, I think it should come out around 1.79 hertz, which is option D. So again, yeah, this is a straightforward formula question. I'll not go into the theory. You can do that in the theory lectures given by Professor Shantanu. So let's move ahead. Okay, so yeah, one of the topic that we left in the previous lecture was the finite state machine. So I've got some basic question just to clear your doubts about the Mealy and Moore. So we have two types of finite state machines. One is what we call as Moore machine, and one be what is called as Mealy machine. When people call it some different names, the pronunciation can be different. Some call it Moore machine and Mealy machine. So the basic difference between a Moore and a Mealy machine is the Moore machine is only a function of the output of the Moore machine is basically only a function of the state. I hope you already are aware of what is a state now, since we have been doing the flip-flops from a long time. And the output of the Mealy machine is a function of both state as well as input. So for example, so this is a way to represent a Moore and a Mealy machine. So this is what we call as a state transition diagram. So in the circles, whenever you see circles with, let's say, a name written as ABCD, so in this particular diagram, ABCD are the states. And since we have four states, so these states are represented by 2 raised power 2, that is 4 states, which is 0, 0, 0, 1, 1, 0, 1, 1. So in this example, you see the state A, whatever you see at the above the arrow is the input, and whatever you see below the slash is always the output. Is this thing clear what I just said? So states are always given as ABCD. Whatever you see above the arrow is the input, and whatever you see divided by is the output. Is this clear? So basically what this particular thing means is, at state A, when the input is 0, it goes back to the output of 0. So basically this particular thing, we can clearly see that the output, that is 0, is only dependent upon the state, right? It is not dependent upon the input. So this is nothing but a Moore machine. Let me give you a very basic example. So let's say if maybe it's something like this, ABC, and if it is something like 1 by 0. So now we can say from state A, the transition from state A to state B, when the input is 1, the output is 0. So here the state or the output is basically a function of both state as well as the input. So this is a Mealy machine. Is this basic difference clear to everyone? Okay. So we can clearly establish that this is not a Mealy but a Moore machine. So first cannot be correct. Yes.
Sir, please repeat one more time.
Okay, sure, sure. So what I'm trying to say is, whenever Okay, just to understand in the simpler terms, whenever you see a state and a output together, that is always a Moore machine, because your state or your output is directly dependent upon the input. That is what I said just now, that the output is only dependent upon the state. It does not bother about the input. And for example, if, as I said here, let me rewrite it. If it has, if it would have been written like this, something like that, could be anything. So let's say any connection. So now here, what this particular diagram says, that when the input is 1, the state transitions from A to B, then the output is 0. Does this line make sense? When the input is 1, which is this, the state transition from 0 to, from A to B. So it is dependent upon the input, then the state as well, and then the output is 0. Is this thing clear to you?
Yes, sir. Thank you.
Yeah, yeah. So then it is a Mealy machine. But in this particular case, it is not happening like that. So this is a Moore machine. It says a minimum of 4 flip-flops are needed to implement. So since we have 4 states, so let's say n states, we require log to the base 2n flip-flops. It is same as we have done before. So 2 flip-flops can basically do the 4 states. Sorry, I think I've written it wrong. So let's say if we have n states, that is 4. So yeah, it's correct. So for 4 states, we require 2 flip-flops. So this is also wrong. It says the logic detects a sequence 110, and the one other option is 100. So to just check that, what you need to do is you need to follow the all the states, and you need to stop where the output is 1. So basically what I'm trying to say, you see here the output is 0, here the output is 0, here the output is 0, here the output is 1, right? So for a sequence detector, you need to follow the shortest path so that you reach to the output 1. So this is A to B, B to C, and C to D. So this is basically a sequence detector. It is detecting this, and the sequence that we have is 1, then we have a 0, then we have a 0. So 100 is getting detected. Is this clear to everyone? You need to start with the first state and you need to go till the output is 1. You will only see single state as output in the Moore machine. Please let me know if this is clear. So the correct sequence is 100. So this is correct and this is wrong. Now it says the state B and C correspond to the detecting pattern of 1 and 10. So let's say it is asking till state B, what is the sequence detected? So you can do that. So from A to B, the sequence detected is 1 only. So which is 1 given here. From C. So from A to C, if you go, maybe I can use some different thing. Yeah, so from A to C, if you go, it's something A to C. So the sequence detected is 1 and then 0. So 10 is the given. So this is also correct. So 4 and 5 are correct, which means option D is the correct answer. Please let me know if this is clear to you all. Okay, if this is clear, let me know the answer to this quickly. This is the same problem, just some different diagram. You can take maybe 2 minutes and then let me know the answer. Okay, let me do it side by side. So is it a Mealy or a Moore machine? Please let me know quickly, is it a Mealy or a Moore machine? Is it not clear or? Okay, so we can clearly see that the state is only dependent, or the output is only dependent upon the state. So this is a Moore machine. So this is exactly similar as we have done before. So first option is correct. Says it's a Moore machine. It says a minimum of 5 flip-flops are needed. So we have 5 states. That means we require only 3 flip-flops. So this is wrong. Then it says the logic detects the sequence 1100. So we'll do it again. We'll go from A to E, and this is the one. So 1, then we have 1, then we have 0, then we have 0. So the logic detected is nothing but 1100. So we have 1100, which is option here. 3 is correct, fourth is wrong. Then it says till B the sequence is 1. So till B the sequence is 1, which is correct. And till C the sequence is 10. Okay, so till C the sequence is actually 11, right? So this is wrong. So this is also a wrong option. This is also a wrong option. So first and third are correct, which is option C. Is this clear to everyone? Okay, let's move ahead then. Okay. So it says the following state diagram is a dash model and it corresponds to dash sequence detector. So take maybe a minute and let me know quickly. Is it a Mealy or a Moore model? It's a Moore model, right? So Mealy cannot be the answer because again, so we need to do the sequence detection, right? So we'll again go. So F is 1. We'll start from A. So maybe I'll highlight it again. So we have 1, sorry. So we have 1, then we have 1, then we have 1, then we have 0, then we have 1. So we have 1, 1, 1, 0, 1. 1, 1, 1, 0, 1. Yeah. So option B is the correct answer. So yeah, let's move ahead. Okay. So this is actually a very good question and it might take some time to do it. So let me try to do it by myself. So it says consider the state transition diagram given below. If D flip-flops are used for the realization of the circuit, then which of the following are true? So here you see the input is a function of both, the state and input. Uh, the output is a function of both state as well as the input. So this is a Mealy machine now, right? So we need to do it. So the way to do it is we have 3 steps. The first step is make the state table. I'll let you know what is the state table. The second step is make excitation table from state table. And the third step is truth table of flip-flop. Yeah, so this is, I mean, this is very basic step. So let me do it and you will be able to understand what I'm trying to say. So first I'll make the state table. State table contains the present state, contains the next state, and both are dependent upon the input. So next state can be when input is 0 or 1, and it also contains the output, which I'm denoting by Y here. So again, it's 0 or 1. So let me try to explain it. What do I mean by that? So let's say the present state, it can be A, B, C, or D. There are 4 states here, which is nothing but 0, 0, as I said, 0, 1, 1, 0, and 1, 1. So please pay attention here. So it says when present state is A and the input is 0. So here you see when the present state is A and the input is 0, the output is 0 and the state comes back to A, right? So it says when the present state is A, the input is 0, then the next state will also be A and the output will be 0. Are you able to understand this? A and 0? Please say yes or no, because this is the main thing. If you understand this, then you will be able to do the problem. Maybe I'll explain one more time. So it says when the when the present state is A and the input is 1. So when the present state is A and the input is 1, the output is 0 and the state transitions from A to B. So it next state is B, but the output is 1. Sorry, the output is still 0. Output is always written in the denominator, my bad. Is this clear? AB00? Yeah, great. So I'll do the same for all. So it says B. So B, when the input is 0, the output is 0 and it goes back to A. So it goes back to A and the output is 0. So when the input is 1, which is this, it goes to C and the output is 0. Similarly for C, when the input is 0, the output is 0 and goes to D. And when the input is 1, the output is 0 and it goes back to C again. And D, so when the input is 0, the output is 1 and it goes to A. And when the input is 1, the output is 0 and it goes to B. So this is the state table. Is this clear to everyone? Okay. So now we'll make the excitation table. Excitation table contains the input. Okay, let me make it in the next. Yeah, it will take a lot of space. So it has an input, it has, so as you can see, the B and A are the states of the flip-flop. So I'm writing capital B and A as the names. So what I'm trying to say is basically this A is 0, 1. I hope you already know that. This is 1, 0, this is 1, 1, this is 1, 0, this is 0, 0, this is 0, 1. Yeah. So we have the excitation table, we have the input, then we have the next state, then we can have the output, and for the flip-flops, we can have DB and DA. So we can again have, okay. So we need to find now. So we can clearly see, so 0, 0 is A, 0, 1 is B, 1, 0 is C, 1, 1 is D. So again, this is A, B, C, D. So what I'm now trying to say, when the input is 0, the present state is A. So this corresponding, when the input is 0 and the present state is A, right? Then the next state also comes as A, right? So it should be 0, 0 and the output is 0. Is this 0, 0, 0 clear to everyone? One more example. When the input is 0, the state is B. The state is B, the input is 0, which is this. The next state is A, so which is 0, 0, and the output is 0. Is this clear? Say yes or no, please, quickly. Okay, great. So now, yeah, we can go ahead. So when the input is 0, state is C, so C goes to D, output is 0. So 0, 1 I can write directly. So C goes to D, which is 1, 1, and D goes to A, which is 0, 0. You can recheck later. I'll just doing it now quickly. Sorry. 0, 0, and the output is 1. So A, when the input is 1, goes to B, which is 0, 1. The output is 0. B goes to B, C, yeah, C, C, yeah, okay. So it should be C, D goes to B, which is 0, 1, and the output are 0, 0, 1. 0, D goes to, yeah, output is 0. So once you solve this, you will get this thing. And since we have a D flip-flop, what is the formula for D flip-flop? DB will be Pn plus 1, right? Because D flip-flop itself is the answer. Qn plus 1 is T. And this will be An plus 1. So I'll write this again. So this is 0, 0, 1, 0, 0, 1, 1, 0. And we have 0, 0, 1, 0, 1, 0, 0, 1. So yeah, we just now need to find DB and DA in terms of input and A and B. So we can do that by using K-map. So let me do that also. So this is X bar X. Then we have B bar A bar, B bar A, B A, B A bar. So it's D. Let's find the DB first. So it's 0, 0, 1, 0, 0, 1, 1, 0. Okay, so we have this and this as singlet. So we can write DB as A bar B plus X B bar A. So we have option like that. A bar B plus X B bar A. Yeah. So this is correct. I mean, I don't see any other option like that. So similarly, we can also calculate DA. You can make the K map. I'm not making it, and you can calculate the Y directly. So this is Y, which is this term. So Y is directly, you can say it's input. Input is X bar AB, which is, yeah. So option D is the correct answer. Yeah, I think we can move ahead quickly. Okay, so we have again the X is the input sequence where Z is the output sequence shown below. Which of the following option correctly describe the output sequence? Okay, yeah, this is again a very similar question. So we just need to make the table and we'll be able to do that. So this is a Mealy machine because the input and output are written outside. So what I can make is input, let's say the state, the output. So the input is already given in the question, which is this. So I'll write this 1, 0, 0, 1, 1, 0, 0. So we'll start with A. So it says when the input is 1, which is here, the output is 0 and it goes to S1. So I'll write, okay. So let's say the state is initially S0. So it will go to S1 and the output will be 0. Right. So now it is at S1, the input is 0, which is this, right? Which is this line basically. So it goes to S2 and the output is 0. Now it is at S2, the input is 0, it says. So which is that, oh, which is this line. So the output is still 0 and it is still at S2. Now the input becomes 1, which is this line. So it goes to S4 and the output is 0. Now it is at S4, the input is 1. So it goes to S3, the output is 1. So now it is at S3, the input is 0, which means this line, it goes to S5, the output is 0. Then it is again 0, so which means this line. So output is 0 and it goes to S2. Is this clear to everyone? The table that I have just made? Yeah, so great. So the output will be this, which is option last. I mean, yeah, option D. Is there any doubt in this particular question? Okay, so if not, I think, yeah, these are all the questions that I had. So we have covered all the topics till I think week 9 in week 8 itself. So you can maybe take a peek again at these FSM questions because these are quite, I mean, this is an important topic and these can be quite confusing if you are not able to understand the concept. So you can take a look at again at the YouTube video. I'll be sending the link quickly. And I've also covered all the DAC and ADC's question. So maybe in the next week we might be starting with our memories, or we'll see that what's the assignment will hold, and we'll see accordingly. So till then, yeah, I think that's it from my side. We'll meet next week same time. Thank you everyone for joining.